mais on démarre à 15. Guys, just before we get started, if you're in the first session for papers and your slide is not in this folder, that's a problem, okay? So if you don't see your slide in this folder and you're talking in like 15 minutes, you want to fix that, okay? Thank you. T'inquiète, là c'est easy. Okay, hi everyone. Welcome to SMC 2022. Thank you. We hope you had fun last night with a cocktail and the concert despite the technical difficulties, you know. So this is also part of our new world, right? Like where we need to wait on people to connect to Zoom and for sound to actually work on Zoom, you know. So that's literally what happened yesterday. So I don't know. Maybe it's some food for thoughts, you know. Like I think that live concerts with real musicians on stage is actually a pretty cool thing, you know. And so people should probably keep that in mind. Anyway, I'm gonna make this short, you know, like it's not like yet another speech or whatever, we already did that yesterday, but this is more like a technical speech to sort of give you an overview of the program of the conference and also an overview of how things are gonna work during the week, okay? So the first thing is internet access. So if you have a computer, you probably noticed that there is EDU Roam. So if you have an institutional account you can use your institutional account to connect. If you don't have an institutional account, you can connect to UJM Invité. Okay, that's the name of the network. And then there is a login and a password. Login is SMC_BZR. It's French handwriting, I know. And then capital R, 3, F, capital G, C, D, capital N, capital W, L, W. Okay? So that you should be able to connect to the internet. You probably already noticed too that there are power outlets under the seats in the venue. So if your computer is running out of power, you can probably connect to one of them. Okay. Great. So I'm just going to give you a very brief overview of the program. So summer school is over. The International FALS conference is over as well. Okay. We had the welcome reception and the first concert. And this is Wednesday, this is today, and so we just did conference registrations, and this is the opening speech. So, as you know, all paper sessions this year are happening as hybrid oral/poster presentations, okay? And this was to sort of facilitate the hybrid format of the conference because a lot of people are attending remotely. Okay, so we just thought it would be kind of a better way to do things. Okay, so for oral presentations, your presentations should not exceed 5 minutes. Okay, you already know that. So 5 minutes max. No questions. It's like a poster craze, but with sort of longer presentations than what you get in a normal poster craze. Okay, so 5 minutes oral presentations, no questions. All your slides need to be uploaded on the drive. You had the link, so you probably know where to go for this. Okay. Once everyone is done presenting an overview of his paper as an oral presentation, we'll all go back in the lobby where the poster session will happen. Okay, and then we just encourage everyone to talk to each other. Okay, because that's the point, you know, like so that you're not just stuck in a room for the whole day listening to people talking, like you want to interact, okay? As part of that, there is something important that I want to say. So there is going to be coffee and croissant, pain au chocolat, blah, 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 during the whole conference. Also, to make sure that you guys have fun and actually talk to each other, there's going to be also beer and wine served the whole time, okay? For free. So we didn't install that yet because, you know, it's a little bit too early, although, you know. Anyway, so eventually, like probably around 10 a.m. this will be ready. There is a fridge. There is a fridge in the lobby. The fridge will always have like cold beer and wine in it if you want to take it. Okay, so it's... Thank you. Anyway, so for hanging your posters, there's always like poster helpers. So for this session, the main poster helper is Remy and Luna. So like if you have questions for hanging your posters and if you need like special equipment or whatever, you can ask them. Okay. Another thing that I want to say is that for people who are attending the conference remotely, there is a Zoom session which is assigned to every poster. Okay, so it would be very nice if at the same time as you're presenting your poster, you have the Zoom session open in case people who are attending remotely want to ask questions. We know it's not super convenient, but it's kind of the only way to do it. So as part of this hybrid thing, you know, like so as you're presenting your poster, you probably want to have your laptop open with a Zoom session on, so that people attending the conference remotely can ask questions. Okay. The session chair for this first session is going to be Pierre Lecomte, and he's just going to make sure, basically, that you guys don't talk more for than 5 minutes. Okay, so once again, no questions. Questions happen during the poster session after that. So there is going to be keynotes, there is going to be industry talks, there is going to be lightning talks, and just a lot of poster/paper sessions throughout the day. Today, at the end of the day, at 6 p.m., we're all going to meet in the lobby, and there's going to be buses that are going to take us to the Corbusier Church in Firminy for tonight's concert. The church is not in downtown Saint-Étienne, so we need to get a bus to get there. It takes approximately 20 minutes. So we all take the bus, go to the concert, and then there's a bus which is taking us back here, basically, okay? In the center of town, okay. So not here, back in the center. Good point. As part of the concert tonight, there is going to be a tour of the church with tour guides and everything. You know, so there is going to be 1 hour so that you can sort of float around. The concert should be pretty short, so we should be back here before 10. Basically, back in the city before 10, so that you can just go to bars or back to your hotel or whatever. Okay. So. There's going to be a special session for young researchers happening on Thursday. It's going to be in French, and this is going to happen in parallel of the conference at the CSI, which is the building, actually, maybe if I click on this, we can see it on the map, but basically, just so that you know where we are. So currently, we are here. This is Saint-Étienne Télécom, okay? And if you just walk down this street, this big building, which has like this metal thing on top of it, you really can't miss it. Like when you exit Telecom from this side and you look on the right, you see this building. It's a super long building with a metal floor built on top of a stone floor, okay? So that's where the special young researcher session will take place. Okay. So there is going to be a concert on Thursday. The concert on Thursday is going to be at the Opera House. You have to get there on your own. It's a bit far from here. So from here, it's like a solid 35 minutes walk, and it's uphill. Just so you know, and it's really uphill. So this concert should be really cool. It's with the Ensemble Orchestral Contemporain. It should be fairly short as well. There is going to be a first one at 6:30 and another one at 8, and the one at 8 will only last approximately 45 minutes. Okay, so this concert is part of your conference pass. Okay, if you didn't pay for the conference because you're only attending the conference, you should actually get your own ticket to go to this concert, because this is like a special concert at the opera. So if you have a paid conference pass, you can go to the concert. But if you have like a free conference pass, and if you want to go to this concert, you should go on the Gram website and actually book a ticket, like buy a ticket to go to this concert. Okay? What? 20 euros. Okay, so you know that in parallel of SMC, there's workshops for kids in schools and stuff like that. So if you want to go check that out, it's starting on Friday, and it's going to happen at the Comet where we were yesterday. So all the things in gray are for like kids or people who don't know anything about computer music or music technology. So if you want to check that out, you can go at the Comet, and this is taking place in parallel of the conference. Okay. So on Friday evening, we're going to have the banquet. The banquet is happening here, okay? The weather should be beautiful. It's going to be much warmer than today. And so hopefully we'll be able to do it outside in the yard, okay? It's going to be great. There is going to be like local traditional music and dances and everything. And there is even going to be someone to actually teach you how to dance those dances. You know, like so this is going to be fun. This is going to be like a traditional menu from my village. Like the cook comes from the village, so like this is going to be like special. So please make sure that you come to this. Finally, on Saturday, there's going to be a concert at the Fil. The Fil is very close to here. It's literally on the other side of the street. And this concert will feature a special session on live coding. So it's going to be a more like a club sort of setting, you know, like with beat music, you know, and there is a bar there, and this concert is going to be longer, and it's probably going to last until like midnight or 1 a.m. Okay, and then we will be very, 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 very tired. I mean, we're kind of tired already. I just want to say that there is an installation at the Fabrique de l'Innovation, which is the building I just told you about, like the one with the metal roof. This installation will be just running the whole time, and there are signs to actually get there. You know, like, you know, it's an installation by Arne Eigenfeld. So yeah. Anyway, I invite you to walk around the city, just like check the touristic spots, you know, and you know that the design biennale is happening in parallel of the conference. There are a bunch of very interesting museums in Saint-Étienne, like the Museums of Contemporary Art, which is not too far from here. It's one of the largest one in France, so it's a cool place to visit. There's also the Museum of Art and Industry, where they have like bicycle collections and like guns and stuff like that, because the gun manufacturing industry was pretty big in Saint-Étienne, so it's kind of the main place for that, actually, you know, like until not so long ago. So if you want to check that out, please do it. You know, I can, and if you have questions, we're here to help. Anyway, I will now shut up, and I think we're going to start the first paper sessions. If you have questions, you can ask them to us directly. We hope you're going to... Oh, one last thing. Lunches, because that's important. You guys probably want to eat at some point. So you got lunch tickets, right, as part of your kits, and like your conference kits. We'll tell you where lunches happen. There is a restaurant in this building, so it's happening in the restaurant, okay? And this is included as part of your conference registration. Just one small thing, though. Please make sure that you don't go there all at the same time, because there is going to be a big line, okay? So you know, there is plenty of time for lunch during the day, so make sure that you sort of try to, there is no easy way to do this, right? Like, so don't go there all at the same time, otherwise they're going to be mad, okay? And you're going to wait. So take your time, you know, and have fun. Anyway, we hope you have a great conference, and we're going to start with the first paper session of today with Pierre Lecomte. Thank you very much.
All right, thank you. So I'm Pierre Lecomte, and will be the chair for this morning. So make sure you keep it under 5 minutes, and I'll show you when you have 1 minute left, and then I run a countdown. So the first paper for this morning will be emulating diode circuits with differentiable wave digital filter from Jatin Chaudhary and Christopher Yuan Clark. So if they're coming. Perfect. Fine, good, new. So go on.
So just want to download?
I'll just download it. I'll just do it like that. You can do it full screen.
I think just I would just to make sure that it looks good.
Okay.
Like maybe it's just shit. Just because otherwise you're not going to be able to do full screen. So,
Okay. Cool.
yeah. So there we go. Or actually, maybe I think if you open them here, tools,
Maybe in the view.
view full screen mode. Yeah, there we go.
There you go.
Okay,
Fine.
Good. Yeah.
Okay, so let's start.
And then switch to you.
Yeah. Okay.
Right. Oh, should we use the microphone or should we just...
No, you have microphone.
it's
there.
here. Okay,
Okay.
cool. No. All right. Hi, everyone. So I'm Jatin, and this is Chris. And we're going to be talking about differentiable wave digital filters.
So wave digital filters are a way of modeling circuits that allows you to kind of separate your model into the different circuit elements. So you have your resistor and your capacitor and things like that. And in the previous literature for wave digital filters, everything is kind of physically modeled. And so our idea was to say, well, let's say you have the physical circuit and you have some data that you've measured from it. How could you use that data to improve your model? And typically this has been a challenging problem because wave digital filters uses a transformed sort of variable to process signals. So instead of voltage or current, which you could measure from a circuit, you have to use these wave variables, which are a little bit harder to sort of figure out what they are at any point in the circuit. So our solution was to basically implement a wave digital filter system using TensorFlow so that the whole processing graph can be differentiated automatically. So that way, if you have some data, you can basically optimize any parameters inside your processing graph using that data and using this automatic differentiation. So kind of a simple test of that we did was to basically try to estimate a circuit parameter using some data. So this is a voltage divider where the data was collected from a circuit with a voltage divider that had two equivalent resistors. And so we basically created an example wave digital filter with two very different resistors. And as you can see, over 100 sort of epochs of optimization, the resistors converge to the same value. And then another very similar example was just using a low-pass filter. So the example low-pass filter circuit had like a 1 kilo ohm resistor and a 1 microfarad capacitor or something like that. And over the course of training, the values of the components in our model converge to those values as well. Yeah.
Okay, so with the diode models, usually in, I guess, most white box paradigms, the nonlinear element is not too easy to deal with sometimes. So it might be computationally expensive, it might not be too accurate because of traditional electrical models. So we decided to use the wave digital filter, and then for the nonlinear bits, we take it out and we replace it with the neural network. So we recorded some real world data, we designed a PCB, we used proper shielding to cover all the EMI and everything. And we can, because of the way we structured this, we can have the entire wave digital filter graph as one model with the dense neural network inside the wave digital filter. So then you can backprop in and out of the wave digital filter graph. And so we pre-trained the diodes first on synthetic data generated from SPICE using the Shapley model. And so after about 2,000 epochs, we got 2,000 epochs, right? We got a good pre-training set, so that brings the network sort of closer to the target first before actually starting on the real world data. And lastly, we then use the real world data to train the network, and which then brought us closer to it. As you can see, the actual transconductance of the diodes is very different from the Shapley model, what the Shapley model initially presented us it to be. Is that one? All right, and this is the final results, where you can see at the left-hand side, the target is the one in blue, and that's the real-world data, and what the Shapley model predicted is the one in orange, which you can see there's quite a bit of discrepancy there. But after some training, our model estimated the target output really well, and it gets really close. Yeah, I think so. Yeah, and we have a real-time plugin that you can download on GitHub. Feel free to have a look and ask me some questions later on. Thank you very much.
Okay, thank you. 4 minutes 30. Okay, so the next one will be approaching spatial audio processing by means of decorrelation and ring modulation in ambisonics by Paul Gutmann and Alain Bonardi. Hi, Paul.
Oh.
Hi.
Parce qu'il a fermé le... Il a fermé le truc.
Like, when you're done presenting, don't close the Google Drive, please. Thank you.
Ah, pardon, c'est paper. Voilà, tiens. Tu télécharges. Si tu vas là. Ouais, non, là. Voilà. Modularity. Ok.
Okay. Hi everyone, I'm Paul Gutmann, PhD student of Graduate School Artec and Paris 8 University. I do research on space representation for spatial audio processing with a research creation practice coordinated by Alain Bonardi and Anne Cédès. Today I present a work we did with Alain Bonardi on two processes in high order ambisonics, which are the decorrelation and the ring modulation. Between 2012 and 2015, Guillaume, Paris, and Colin Francesco developed the C++ library HOR for Max, MSP, and Pure Data, a library which gathers spatialization tools using the high-order ambisonic model. The developers had the possibility to apply processes well known in electroacoustic as granulation, modulation, decorrelation into the ambisonic model between the encoding step and the decoding step. Unfortunately, the PD version is obsolete since 2019, and in order to formalize 20 years of work on mixed music and to address the obsolescence of HOA on PD, Bonardi began to transcribe the processes in Faust, grouped in ABC library. In this context, we began to add new developments and fine-tunings to these two processes. The decorrelation and the ring modulation in ambisonics allow compositors to go progressively from one localizable source to a processed sound field, diffuse sound field for the decorrelation, and complex movement in space for the ring modulation, just by controlling one meta parameter, the factor of diffusion and the factor of modulation. Ambisonic are a set of techniques to record, synthesize, and reproduce sound field based on 3 steps: encoding, decoding, encoding optimization, and decoding. The encoding step consists in the description of the sound field with elementary component called spherical or circular harmonics. And the decoding step consists to applying the matrix depending of the loudspeaker setup to reproduce the sound field encoded before. In our approach, the processes come between the encoding and the decoding step. Two modes of processes coexist, the scene and the effects. The scene mode allows to synthesize directly one mono source without a step of encoding in ambisonic. In this case, the sensitive effect goes from a large mono to a processed sound field. And the effects mode, which apply processes to each ambisonic component after encoding a source in one direction or a recorded sound field. With this work, we want to improve the possibilities of these processes already there in the version C++ of the library and their sensitive result. The idea is to give a smoother sensitive result when the factor is manipulated and an easiest access to these tools for musicians. Plus, we want to highlight the richness for creators involved in digital frameworks to handle and explore all layers gathered in the digital object used for the creation. How did we do that? To make this research, we used an iterative prototyping loop going back and forth in our studio at the Maison des Sciences de l'Homme, Paris Nord, to try in situ and listen the result. Plus, I handled the decorrelation in personal composition, and we had feedback from advanced artists and students of the Bachelor of Paris 8. The research creation here means that both parts emerges and merges with the other. It's very important for us to handle and test the tools we developed with a practice of creation. What's the deliverables? Since a few weeks, the ring modulation and the decorrelation are included to the standard library of Faust, HOA, with two modes, FX and Sin. And the user interface part, which give an easiest access for musicians to handle these tools, are in the ABC library. There is also audio example with a binaural version of my electroacoustic work, initially for 16 loudspeakers in 3D, compression, dilatation. Thank you for your attention. It will be a pleasure to discuss this work beside my poster.
Thank you, Paul. So the next paper will be Modular Physical Models in Real-Time Interactive Application by Sylvain Willemsen, Titas Lassikas, and Stefania Serafin.
This one? Oh, it's yes, well, and then this folder. Yeah. Ooh. Spoiler. There we go. Cool. All right, hello everyone. My name is Sylvain Willemsen, and together with Titas Lassikas and Stefania Serafin, we submitted this paper titled Modular Physical Models in a Real-Time Interactive Application. And what we used for this application was we made use of modularity of musical instruments. So take, for example, a violin. We can decompose this violin into several smaller resonator components, such as 4 strings, a bridge, and a body, for example. But the nice thing is that we can also use these components to create different instruments. For example, a guitar consists of slightly different parameters and geometries, but the same essential components. So 6 strings, a bridge, and a body. And in our application, we model all of these components separately using a technique called physical modeling, as many of you will probably be familiar with, which is essentially a software implementation based on physical processes. So looking at the physics of the strings, the bridge, and the body, connecting them and implementing them in software. So what this means in terms of our strings, bridge, and body is that we look at their descriptions as partial differential equations, which I will not go into depth here, obviously, but we can model these components in isolation using these equations and discretizing them. So now that we have those components, we need to somehow model their interaction. So how does the bridge connect to the body, for example? And the way we do this is using connections, which we can make to be rigid, linear, or nonlinear. And this is the general nonlinear form. So that is what our application is based on. So now we only talked about resonators, which in essence do not make any sound until you excite them. And usually the bow is excited, or the violin is excited with the bow, a marimba, for example, with hammers, and the guitar with a pick. And usually these are grouped together in the physical world. But now that we're in the virtual world, if we model these things, these boundaries kind of get grayed out, and we can start switching around these exciters. So we can, for example, now bow the marimba, or hammer the guitar, for example. So based on all of this, we created this application, this VST, where you can build your own instrument, essentially, based on all these principles. So it's divided into an instrument area, an excitation panel, and a control panel. And here we loaded in the guitar preset, so we can see 6 strings, a bridge, and a body, which are all connected together using either spring-like connections or rigid connections, as shown in orange and green here. Then we can see here an exciter module, which in this case is the plug, but we can also change that to be a bow, for example. So maybe it will be better for you to see a demo, and I hope that the sound works, and the internet as well. Let's see. Yeah. So now I just added a string module. And we can add another string module which has a fundamental frequency that is twice that of the original string. And we can plug both of these guys. Then we can add a plate, which functions as a body, even though it's very metallic now. But now we can start to connect these guys with some rigid connection, a nonlinear connection, for example. And the fun thing about these nonlinear connections is that you get these pitch glides. That the more amplitude there is, the more force there will be on the spring. We can also change the exciter module to be a hammer instead, or of course the bow. With which we can also excite these guys. Yes, then we made also several presets, such as the guitar preset that you saw before, which is tuned to be sounding like a guitar. And we only now hear the output from the body, so the connections really put energy to the body. Yes. Cool. So this is our poster. Come and find us, and I thank you for your attention. Thanks a lot.
Thank you, Sylvain. Right, so thank you, Sylvain. The next paper will be rubbing a physics-based synthesis model from mouse control to frictional haptic feedback by Marius George Onofre, Federico Fontana, and Stefania Serafin.
Because if you do that, it's going to stop the stream. So you need to use this computer. Presentation.
Yeah, because Marius couldn't take off yesterday.
Yeah, no, like, because you really can't plug that out. It's going to break the whole system.
Okay.
Shit. Can you send it? Can you, like, put it on a drive? Send it to me. Actually, can we? Okay, someone else is going to talk. You send this to me on a drive.
Okay.
Sorry about this.
Okay.
All right. So while Federico is uploading his slides, so let's switch to the next one, which will be 1EOA, a computational approach to rhythm training by Noel Alben and Ranjani HG. I don't know how to pronounce, sorry.
This one? Yeah, this one. View. Oops.
I think I'm in the presentation. It's fine. Yeah, it's fine. Hi guys, this is a presentation on 1EOA. Our goal was to build a rhythm learning application that is mathematically informed and perceptually relevant to human perception of rhythm patterns. And we basically built a proof of concept of a system that is able to assess learners' performances, and then based on that assessment, give them a next highest complex rhythm pattern, and basically have a teacher-learner relationship wherein the system continuously provides you a new pattern of increased complexity. So the system overview is pretty simple. It has three parts: the pattern generator, the user's recorded input, and the performance analysis. Within the pattern generator, we use binary sequences of complexity of patterns, and they are mapped to certain complexity values, and they are sent to the pattern generator, which I will talk about more in the next slide. And the performance assessment is linked to the user's feedback, and it is all tied up into a web application. So for the pattern generation, we basically generate an isochrone for a particular tempo and particular rhythmic pattern, and we use a representation of binary ones and zeros for the pattern, and based on what it is, you get that kind of a particular impulse, and then using an impulse response, the isochrone is convolved to give us the particular sounds that we want. And for the performance analysis, we basically look at your performance over 4 bars and give you a particular deviation in terms of your timing deviation from what is actually required by the pattern and what you have performed. And if it is if it's within certain error requirements, we will let you proceed to the next complex pattern. This entire thing is based into a website where users were able to log in, start their progress, and the website would remember where they stopped last, and then it continuously gives them patterns based on a new complexity value. So the complexity metric was based off of Whitson-Todd perceptual analysis paper, where a series of tones and non-tones were generated using this complexity metric of entropy and uncertainty that was calculated on these sequences of codes and tones and non-tones. This was translated to binary patterns of ones and zeros, where ones represents an accented note and zeros represent rests. So it's a perceptual coding process that essentially breaks down these sequences into certain code levels, and at each code level we basically calculate 2 uncertainty values, and the combination of these uncertainty values at the last code level, which is basically when the pattern itself is recreated by the code levels, is basically the complexity value of that pattern. We also ran a small pilot study of about 8 users in which we were able to segregate them based on their years of experience in rhythm training or just musical training in general. And we were able to monitor their progression within cycles of each pattern and increasing complexity values. The system, however, does not test the learner's proficiency across different tempos. Neither does it test for mixed cycles. Basically, it doesn't test for their progression within, okay, they played a pattern in 7s and then to move to patterns of 5s. So it just basically within a particular cycle. So our future work is basically aimed at perceptual evaluation of the pedagogical significance of this complexity metric and building an end-to-end generative algorithm for rhythm using similarity metrics. This is just a proof of concept that mathematical models can be used to help inform computational systems to generate pedagogical systems, which does not require expert opinions or the bias of teachers. So we hope to build a system that is perceptually relevant and mathematically informed to generate its own rhythm syllabus for beginners and professionals to basically practice their rudiments and improve on their timing. Thank you so much. There's a link to my website, and you can find me at my poster.
All right, thank you, Rajani. So let's go back to the previous presentation, rubbing a physics-based synthesis model from mouse control to frictional haptic feedback. You're welcome. Bye, Federico.
Is it?
Okay, so just not to waste time, I'm not Mario Sonofrey, who should take off yesterday, but he couldn't due to an unexpected heavy emergency. So we organized this in the very last minute. Sorry for the discomfort, also to Romain. We are actually seeing a video of the same presentation, and I will also try to demo at the poster session if I'm able to set up as he was. So I invite you to later also join the poster and try to put hands-on on the application that I will be presenting, hopefully right now.
I'll add to this that you never ever want to disconnect the HDMI cable because there is an HDMI splitter, and if you do it, people lose the streaming, and then it takes like many minutes to sort of reboot the system. So like you don't want to unplug this cable.
This recalls our mottos of interaction designers, that problems are opportunities. Okay. Maybe just go.
Hello.
So thank you, Marius.
And I will be presenting a paper called Rubbing the Physics-Based Synthesis Model from Mouse Control to Haptic Feedback. It's a paper I worked on during an Erasmus stay at the University of Udine in Italy. And I worked on it together with Federico Fontana and Stefania Serafin. The paper investigates intuitive controls of a physics-based synthesis model with a desire to include the effect of haptic feedback resulting from the interaction with the model. One such interaction is frictional excitation, where interesting nonlinear effects provide a stimulating sonic and tactile experience. For this, we chose a simple model of a bank of mass spring dampers individually excited by rubbing. Regarding the controls, we wanted to gradually mimic the physical gestural action and preserve a link between instrumental gesture and sound or haptic feedback. 3 control strategies were developed, which I will present shortly, and the user study was then carried out in order to compare the experience of playing with the different devices. The Audio-Haptic physical model app is that of a mechanical mass spring damper excited by a frictional force. This frictional force is modeled by a nonlinear function which scales the applied normal force. The shape of this function can be changed by a dynamic friction parameter A, which controls how sticky the contact is. The real-time implementation was carried out in C++ using the JUICE framework. The GUI of the application can be seen to the right. 11 instances of mass spring dampers are created, tuned to different resonant frequencies. Each can be individually excited with a stick, illustrated as a yellow rectangle when in touch with the masses, or a gray when lifted. Multiple masses can produce sound simultaneously. And finally, 3 knobs controlling the damping, friction parameter, and the global volume are also included. Regarding the control strategies, the goal was, as previously mentioned, to mimic the action of rubbing. 3 control strategies were developed. First was the mouse, traditional human-computer interface. Then there was the SensorMorph, pressure-sensitive touchpad, which allowed more natural application of the normal force. And finally, the 3D Systems TouchX haptic device, which could provide feedback to the applied normal force, as well as frictional feedback resulting directly from the physical model. The goal of the user study was to compare the control strategies and investigate if mimicking the instrumental gesture benefits the experience. In order to achieve this, a combination of quantitative and qualitative methods was used. A questionnaire assessing 7 unique attributes of interests was carried out, while for the qualitative part, we carried out an interview where the focus was on investigating if there was an understanding of the different controls and if haptic feedback played a part in this. We had a total of 14 subjects in the evaluation. Most had musical experience with traditional instruments, but only 1 person used virtual instruments before. Regarding the procedure, 3 instances of the app were open, and we gave an intro on the synthesis model as well as on the controller setup. User would then use the application, and they were free to change between the controllers. When they decided to stop, they filled the questionnaire, and finally a short interview was carried out. The results show a clear general preference for the TouchX. A surprising result was that the mouse was preferred over the sensor, and we also found that users had a better understanding of the friction amount control as a result of the presence of haptic feedback. Yeah, so as conclusion and future work, basically preserving the link between excitation and gesture of the physical system and the resulting sound seems to enhance the quality of the experience. The user study shows a clear preference for controlling the app with the haptic device, and the haptic feedback in the interaction allowed users to better understand the controls of the physical model. Some other ideas are changing the number of masses and their tunings and exciting via multiple sticks, or adding connections between masses, as well as exploring building different haptic devices for control. That's it. Thank you.
All right, thank you, Federico and Marius. The next presentation will be for Lisa, a piano-based sonification project of gravitational waves by Andrea Vallée and Valeria Corol.
we have a connection with Bandcamp? I was thinking.
Bandcamp. Yeah.
Just as like browser audio from the browser, yes.
Yeah, from the browser. Yeah. So
Just Control N. Vediamo if it's easy. Okay. So there, open. Okay, now I don't know where to go. Okay, that's tab, fine. And then
Yeah. No.
no, this one.
Download.
I have to download it.
Download it. Yeah. It's to put it in full screen.
Yes,
This
yes,
folder. No. Here.
Up,
Look.
yes.
Slide
Slide,
down.
slide.
View.
Yeah.
View.
View
Full screen mode.
Full screen mode. Okay. Okay, hi to all. I'm Andrea Valle. I'm presenting here a contribution we have worked on with my colleague Valeria Korol. Valeria, she's an astrophysicist actually working in Birmingham, and as you can see, the title of the presentation is For Lisa, Music Composition from Gravitational Waves. Of course, the title is a pun on LISA, and LISA is the Large Interferometer Space Antenna, which is a project which has been funded by the European Space Agency. And actually it will build something like the largest object ever built, because the idea is to create this sort of triangle above the Earth, with a distance between each couple of points of something like, it's 2.5 thousand kilometers. In order, these three blocks, these three space objects will be sent to space in order to detect gravitational data. Gravitational wave data have been proposed initially by Einstein, but have been detected physically only recently. And as Valeria was a part of this large project, actually these three spaceships should be sent to space in 2025, and Valeria has worked on the creation of data used to in order to test the models that should allow to send these three blocks. And so the project is a very abstract one, because unlike electromagnetic waves, gravitational waves have been conceived theoretically and cannot be perceived directly. So hence the idea to develop a multimedia project, which has been funded by the International Astronomical Union and by the Netherlands Research Council, to provide to general audience a sort of glimpse into this kind of phenomena. And the idea has been to create a performance, a multimedia performance. I've been involved as a composer. You can see in the image right there, we were in Genoa for the premiere. The performance is an artistic performance made up of a sort of installation with the Red Air artist, which is Samantha Stella, proposing a reading of the 100 most visible stars from the Earth, which has been inspired by Peter Greenaway, the film by Peter Greenaway, Drawing by Number, and substantially the core of the performance is a piece for prepared piano that I composed from the data I have gathered from Valeria's research group. So actually the point was to have something back like that image, that greenish image. And from those data, the idea was to compose a piece for prepared piano. I choose prepared piano because piano was a constraint of the project from the beginning, and I decided to prepare it in a sort of crumb-like style with chains and paper. So in the contribution, I would speak about the technique I've used to map those data. There were 26,000 sources of gravitational wave data, and how to map them into music notation. So I'm proposing a 4-stage sonifiers. Substantially, the first stage is used to create a browsable space, the one you saw down there, which I implemented in Super Collider, and then I created sort of trajectories into those spaces with these sources that acts like something like event generators. Once that we have these event lists, the second part of the schema was is used to create automatically the music notation, which is the one down there. So if you come to the poster and if you're interested, I will be happy to explain you how we did this composition process. Thanks a lot. Merci.
Right. Thank you, Andrea. So the next presentation will be sonifying an office gadget to indicate air quality by Rod Selfridge, Carlo Baron, and Sandra Pauletto.
Folder. View. Full screen.
So hello, my name's Rod Selfridge, and along with Carlo Barone and Sandra Pauletto, we're presenting sonifying an office gadget to indicate air quality. So the background in this, we've been working on sort of sonifying air quality and looking at what CO2 does, specifically in offices. If you get too much CO2, you can get something called sick building syndrome, which produces fatigue and headaches and respiratory problems and vision and things like that. So we wanted to see whether we could present that through sound, but also using an office gadget, because office spaces, if you personalize them, it's sort of it's meant to be beneficial for your well-being and your productivity. So an office gadget that you could have by your desk that could sort of tell you the air quality in the room, we thought that would be quite nice to do it through sound as you're walking away. So we could have looked at something like a sort of Newton's sort of swing and at the dipping bird, but I wanted something that I could make and actually control myself. So we built an hourglass. And for that, we can go along and just steal some scrap wood from the workshop and a couple of Pepsi bottles and some salt and stick it all together and you've got an hourglass. Put some photoresistors on it, an Arduino breadboard with a CO2 monitor and an accelerometer. Attach it to a laptop with pure data, add some sounds, and you can then have this office gadget that you can interact with to tell you the air quality. So we tested 4 different sounds to see whether people liked them for clarity and preference. So the abstract model, that was like an FM synthesizer, and the pulsating of it sort of slowed down, sort of whoop, whoop. And then when it got sort of higher CO2, it was a bit more whoa, 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 whoa. And also with the falling sand, we had the frequency of a second model. So it could sort of warn you when the sand's about to fall out, and maybe when you need to interact with it again. Did a musical model, which was the sound of a bell, so the more the rhythm of the bell, the faster it was, the faster the tempo, the more CO2 there is in the room. Again, you can sort of monitor that. A concrete model, which we is based on howling wind, so the faster the wind blew, the higher the pitch, and obviously the bigger the gain is as well, so you can, again, monitor what's going on, with the second one telling you that the sand is falling through. And the cultural model, that was based on my sort of, if the air quality was bad, you had respiratory problems, and the saying, a frog in your throat. So I put frog sounds in there. And then the more frogs the worse air quality it was. And then the speed of a fan slowed down as the sound fell through. And I just basically thought, who wouldn't want to sit and work and listen to frogs? It turns out my participants didn't want to sit and listen to frogs. The frog model was by far the most unpopular for clarity. We can see that the FM synthesizer and the bell and the wind model, there's no significant difference between the clarity for them, but the frog model nobody really got. And for preference, the bell and the wind model were the most preferred by the participants, and the frog was hated, but never mind. So in the future, I think we'll redevelop it so that we can maybe do a hybrid of the bell and the wind. Naturally, we would use Bella and have it standing alone rather than connected to a laptop. And that's where we're going to move on with that. Come and speak to this at the poster and we'll tell you more about it. Thank you very much.
Thank you, Rod. The next presentation will be a perceptual study of sound ecology in peripheral sonification by Maxime Poré, Catherine Semal, and Myriam de Sainte-Catherine.
Like, if I can just say one thing, like, if you could have all your slides ready before the presentation for the next one so that we download everything all at once, that would be great. Like, so please have your slides ready, like, before it actually starts. Then we download everything and then it's too late, okay? Thank you.
Okay, so hi everyone, my name is Maxime Poré and I'm a PhD student at the University of Bordeaux. I'm here to tell you about some experiments I've been doing with my co-supervisors on some psychoacoustics and especially reacting to various types of sounds in peripheral process monitoring sonification. I'll do a little bit of contextualization on the case study that this is applying to, but ultimately we found that the more interesting aspect of this paper was more the hypothesis and the methodology, so I'll go over those as well. And then I'll end with an overview of the results and some discussion and future works. So the case study for this experiment is a work that we've presented actually at SMC-2021 last year, which is a 3D printing process, a somewhat generic industrial 3D printing process in which you want to monitor some geometrical data and some thermal data. And our hypothesis back then was that we could possibly create a soundscape consisting of two different ecological types of sounds. On one hand, musical sounds for geometrical data, and on the other hand, natural metaphors for the thermal data, assuming that possibly it would help the listeners better discriminate between the types of data depending on the types of sounds that they would hear. We found that in the usual design guidelines for those soundscapes, it's recommended to have some logical coherency, the famous ecology for process monitoring sonification. But also some other studies seem to suggest that incongruous sounds in some settings could allow for a better reaction and recognition. So we ended up wondering which one would be better. Could we possibly create some kind of experiment to find that? And at what costs, so depending on which criteria should we go for coherent or incoherent or musical or natural and everything. So the first thing we did was create two new ecologies based on the mixed one. We reused the musical sounds and created two new ones for the thermal data, and it created the synth ecology. And on the other hand, we created the nature ecology by reusing the two thermal metaphors and using two new natural metaphors for the geometry. And then we ran it through the same dual task experimental process that we originally used for mixed, so as to be able to compare all of that. And the process, as you can see, consisted in a pretty simple exercise where you could rewrite X and O sequences in the middle. And as you listen to the soundtrack, you had to annotate anomalies that you noticed. This allowed us to gather some data on the way users could still carry out primary tasks while listening to the display, and also how efficient the display itself was at conveying various types of alarms or alerts, whatever. And also we sent the users afterwards a little survey where they could tell us quantitatively by agreeing or disagreeing with a bunch of statements how they felt about the display with regards to the primary task and everything, and qualitatively also tell us just freely how they felt about the displays. This is just a quick overview of the results. Of course, I won't have time to go over them in detail now, but I'll invite you to come to the poster session afterwards. It did help us notice some aspects of the criteria that would favor one or the other ecology. Okay. But ultimately, the experiment would need to possibly be redone in a less pandemic-y kind of setting, where we would actually invite people over and supervise them as they're doing the experiment, so that maybe they better understand the experiment. Because as it stands, the ANOVA we carried out over the results was a bit inconclusive. Some of the user remarks still related to the sound choices, so also maybe get some more sound design work done on the ecologies as they are. And of course, this is just one example for one case study, but we hope that the methodology for comparing sound ecologies that we proposed might be used later in the future, and possibly look out for trends in the results of those studies. Thank you for listening. I was Maxime Poré, and I'll invite you to come to my poster session afterward. Thank you.
Right. Thank you, Maxime. And the final presentation for this morning is Speleoacoustics in Southern Ardèche for Oralization and Music Experimentation by Luna Valentin, Myriam Collard, and Philippe Monteil.
Hi everyone, so today we are presenting on our paper on speleoacoustics. So this paper is based on speleoacoustics fieldwork that we made in 2021. So what is speleoacoustics? First we decided to introduce the term speleoacoustics to speak about cave acoustics, because there was no term for that. So what we did basically is that we made impulse response measurements in Ardèche Valley limestone caves in southern France. We wanted to produce accurate and extensible acoustic data, which would be relevant to human experience of caves. We also wanted to introduce a new methodology for speleoacoustics fieldwork, for exploring, for documenting, and for evaluating the acoustics of caves.
And why caves? Caves have been important across human deep time, and maybe less important to us now, but there was a time when it was the place to go for experiences like we're having today, right? So I work in archaeoacoustics, and Luna's a spelunker, expert spelunker. So we combined forces because Luna is now studying archaeoacoustics of caves as well, and I wanted to extend my work into this deeper time domain. You see here a cave-attired researcher making impulse response claps, a human-produced impulsive signal like a Dirac signal that contains pretty much most frequencies in the range of human hearing and sensation in hopefully almost equal proportion. But one of the things that our research showed was that in fact a clapper doesn't produce adequate low-frequency energy to energize large volumes. So that's something that our research in fact shows, and we can show you details in our poster and Luna will talk a little bit more about that. But also you see a pair of first-order ambisonics portable recorders. Luna will also speak more about how our research was testing the performance of specific kinds of very portable equipment in these high humidity, specifically challenging environments for making acoustical measurements with audio equipment that's not specially designed to resist those environments. So the trick of having two first-order ambisonics recorders with the first channels placed in equivalent positions to a standard binaural array like the ORTF 17 centimeters apart is to actually provide spatial sampling according to possible auditory experience. So that really human centers the data collection proposition. And also we're using an omnidirectional portable loudspeaker. Here it's a Bose SoundLink Revolve 2 plus 2. And this is all, they both are located source of the loudspeaker and the microphone receivers at approximate locations where a human could produce sound, like from the voice or from a wind instrument, which we know are common to, say, Paleolithic sound making in caves.
So one of the goals was in-cave testing of audio equipment and source signal, because of course there are a lot of constraints of taking equipment to caves, like 99% of humidity, the portability of equipment is important. So we've been testing clappers, as Miriam said. We've also been testing sound speakers, but we needed to test how they were powered, how was the battery working in the condition of the caves. So we compared the results between the clappers, between the speakers. We also compared the results of several microphones to see which one are working the best in those cave conditions. And that's what we will present in the poster session.
And also you'll see an interesting innovation with automotive audio, an automotive subwoofer used as a portable subwoofer sound generation source for room acoustics, which actually is quite effective. Yeah, and so at the end, our purpose is auralizing cave environments, creating physically accurate reconstructions of the acoustics of really unique and contrasting geomorphologies that have, and we show in our poster, come see it, really contrasting experiences for the auditory domain that can be quantified using acoustical metrics such as early decay time, the different RT reverb time metrics. So these are things that we wanted to quantify because people comment on them anecdotally, you can hear it, you can feel it, but let's see it in the data, and then let's create data that we can use to reconstruct that in a variety of contexts, whether it's over headphones binaurally or in multi-channel spatial audio, in immersive virtual augmented reality contexts, which are new projects for us working in speleoacoustics and in archaeoacoustics, paleoacoustic of caves, especially in France.
Thank you.
Thank you.
All right, thank you, Luna and Miriam. And now I invite you to go in the lobby to enjoy the poster session.
Bon, bah ça va, c'est tranquille.
Hein?